Introduction. This book introduces a better way to build distributed systems by using the principles that make the World Wide Web the most successful distributed system in history. It's for anyone creating a web API, whether it's for public, internal, or partner use. A major problem with most of today's APIs is that they are brittle and hard to change once deployed. In contrast, the REST architectural style is designed to manage change gracefully. The web itself is a massive, constantly evolving system with millions of websites and billions of users on countless different platforms, and the principles that allow it to thrive can be applied to your API. The book aims to solve two specific problems. 1. Duplication of effort. Many companies design unique APIs for very similar tasks, like microblogging, leading to immense wasted effort. Instead of creating the 58th unique design for a simple problem, developers could reuse existing, powerful standards like the Atom publishing protocol. 2. The misunderstanding of hypermedia. While most developers now understand basic REST concepts like resources and HTTP methods, the most crucial and powerful aspect, hypermedia, is still widely misunderstood. Hypermedia, the use of links and forms to guide interaction, is what makes a system truly RESTful and capable of evolving without breaking clients. This book is fundamentally about understanding and implementing hypermedia. The book is structured to guide you from foundational concepts to practical design strategies, covering various hypermedia formats, design patterns, and the nitty-gritty of using HTTP effectively. It will equip you to build APIs that are not only functional, but also flexible and durable in the long run. Chapter 1. Surfing the Web. This chapter breaks down the core principles of REST by using an analogy everyone understands: surfing the web. Imagine seeing a URL on a billboard for a simple service called "You type it, we post it." Key concepts explained through analogy. Resources and representations. The thing a URL points to, like the home page, is called a resource. What you get back from the server when you visit that URL, the HTML document, is a representation of that resource. You never interact with the resource directly, only with its representations. Addressability. Every important concept should have its own unique URL. This makes it possible to link to, share, and talk about specific things, like a restaurant's menu, without having to navigate through a generic homepage. Statelessness, short sessions. The server doesn't remember you between requests. When you load a web page, the server sends it and then forgets about the interaction. You could leave the page open for months, click a link, and the server would respond as if only a second had passed. This lack of server-side session state is a cornerstone of REST's scalability. The state of your application, which page you're on, is maintained entirely by the client. Self-descriptive messages. The representation you receive, the HTML page, contains everything you need to know to take the next step. The text, links, get started, about this site, and forms on the page describe the available actions. You don't need a separate instruction manual to use a website. Standardized methods. You interact with all websites using a small standard set of actions, or HTTP methods. The most common is GET, when you click a link or type a URL, which simply retrieves a representation. When you submit a form to create something, you use POST. Using a limited, universal set of verbs simplifies the architecture. Hypermedia as the engine of application state, HATOS. This intimidating-sounding phrase has a simple meaning. You navigate an application by following links and submitting forms. The server guides you by providing these hypermedia controls, like A tags and form elements, in its responses. The choices you make determine the state of your application. This is also referred to as connectedness. The semantic challenge. Websites work because a human is interpreting the pages and deciding what to do next. A computer can see a link with the text "Get started," but it doesn't understand what those words mean. The core challenge in API design is bridging this semantic gap so that a software client can make intelligent decisions about which links to follow and which forms to submit, just like a person would. Chapter 2. A Simple API. This chapter shows how the principles from the website analogy in Chapter 1 can be applied to a programmable API. The goal is to create an API that a developer could figure out how to use starting with nothing but a single URL. Interacting with the API. Making the first request. When you have a URL for an API, the first thing you should always do is make an HTTP GET request. GET is a safe method, meaning it's only for retrieving information and won't cause any changes on the server. This makes it a safe bet for exploring an unknown endpoint. Reading the response. An HTTP response has 3 parts. Status code, a number like 200 OK that gives a quick summary of the result. Headers, metadata about the response. The most important is content type, which tells you the media type of the data. For example, application/vnd/collection+JSON. Entity body, the actual data or the representation of the resource. From plain JSON to a hypermedia format. Many APIs use plain JSON, application/JSON, which is a simple format for representing data structures. However, plain JSON has a major limitation. It doesn't have any built-in concept of hypermedia, links, or forms. This is where specialized media types like collection+JSON come in. While it looks like JSON, its structure is constrained by a standard that defines specific keys for hypermedia concepts. For example, href is explicitly defined as a URL for a resource. Items is a list of member resources in a collection. Template acts like an HTML form describing how to construct a request to add a new item to the collection. By using a hypermedia format like collection+JSON, the API's response becomes a self-descriptive message. The client doesn't need out-of-band documentation to know that href contains a link or how to create a new post. That information is embedded directly in the representation. Writing to the API. To add a new message, a client follows the instructions in the template object of the collection+JSON document. It fills out the template with the new data and sends it back to the collection's URL using an HTTP POST request. POST is the standard method for creating a new resource within a collection. When the server successfully creates the new message, it responds with a 201 created status code. The response also includes a location header containing the URL of the newly created resource, which the client can then get to retrieve its full representation. Liberated by constraints. The key takeaway is that constraints are liberating. By agreeing to the constraints of HTTP and a hypermedia media type like collection+JSON, we solve many problems at once. Instead of designing a custom, one-off API that requires custom client code, we can build upon shared standards. This reduces the amount of documentation we have to write and allows users to leverage existing libraries, narrowing the semantic gap between different APIs that perform similar functions. Chapter 3. Resources and Representations. This chapter dives deeper into the foundational concepts that underpin the REST architectural style, resources and representations. A solid understanding of these ideas is key to designing flexible and powerful web APIs. Core concepts. A resource can be anything. In REST, a resource is any concept that is important enough to be referenced. It could be a document, a user profile, a row in a database, or even something abstract like the color black or the relationship between a mother and daughter. The only requirement is that it can be identified with a unique URL. From a client's perspective, you never see the resource itself, you only ever see its representations. A representation describes resource state. When a client requests a resource, the server sends back a representation, which is a document that captures the current state of that resource in a machine-readable format. For example, a pomegranate resource might be represented as an XML document describing its size and ripeness, or as a JPEG image. The same resource can have multiple representations, e.g. JSON and XML. Representations are transferred back and forth. This is the heart of representational state transfer. When a client sends a GET request, the server sends back a representation describing the current state of a resource. When a client sends a POST, PUT, or PATCH request, it sends a representation describing the desired new state of a resource. The server then attempts to update the resource's state to match that representation. The protocol semantics of HTTP. Clients can't just do anything they want to a resource. They must use the predefined methods of the HTTP protocol, which define the protocol semantics, or the high-level meaning of an interaction. The key methods for APIs are GET, a safe method used to retrieve a representation of a resource without changing its state. Delete, an impotent method used to destroy a resource. PUT, an impotent method used to completely replace the state of a resource with a new representation. It can also be used to create a resource at a specific known URL. POST, a method that is neither safe nor impotent. It has two main uses. 1. Post to append, creating a new resource within a collection, like posting a new message. The server determines the URL of the new resource. 2. Overloaded post, a catch-all method for any operation that doesn't fit the other methods. This is common in HTML forms, but should be used carefully in APIs, as its meaning relies on application-specific semantics rather than protocol semantics. Patch, an impotent-like method for making partial modifications to a resource's state, which is more efficient than PUT for small changes. Head, a safe method to get just the headers for a resource without the representation body. Options, a safe method to discover which HTTP methods a resource supports. Impotence is a crucial property. It means that making the same request multiple times has the same effect as making it once. Delete and PUT are impotent. If you send a delete request and the network fails, you can safely send it again without worrying about unintended side effects. POST, on the other hand, is not impotent. Sending the same POST request 5 times will likely create 5 new resources. By choosing the correct HTTP method, you align your API's behavior with a universally understood set of protocol semantics, making it more predictable and easier for developers and tools to work with. Chapter 4, Hypermedia. This chapter tackles the most critical yet misunderstood component of REST, hypermedia. Hypermedia is what connects resources together and tells a client what it can do next, making an API navigable and adaptable. What is hypermedia? Hypermedia is essentially application control information embedded within a representation. On the web, this means links, A tags, and forms, F form tags. These are hypermedia controls. An HTML document isn't just a container for text and images, it's a guide that tells the user and their browser what HTTP requests are possible from that point. An A tag describes a future GET request to a specific URL that the user can trigger. An image tag also describes a GET request, but it's an embedded link that the browser triggers automatically to display the image. A form tag describes how to construct a POST or GET request, often with a custom body or URL parameters built from user input. The key idea is that the server provides a menu of options, and the client chooses from that menu. This is what makes the web so flexible and is the principle that most RESTful APIs are missing. Hypermedia technologies beyond HTML. URI templates, RFC 6570. These are strings like http:/example.com/search/query that describe an infinite family of URLs. A client can substitute a value for a query to construct a specific URL for a GET request. They are more flexible than simple HTML GET forms for creating nice-looking URLs. The link header, RFC 5988. This HTTP header allows you to add simple hypermedia links to representations that don't natively support them, like plain JSON or image files. It functions much like an HTML tag but lives in the headers instead of the body. For example, link less than http:/example.com/page2, rel equals next. What hypermedia is for? Hypermedia controls serve three main purposes. 1. Guiding the request. They tell the client how to construct an HTTP request, the method, URL, headers, and body. A simple link defines the method and URL, while a form defines how to build a custom request. 2. Making promises about the response. They can signal what kind of representation to expect in return. For example, a link with rel equals edit in the Atom publishing protocol implies that the resource at the other end supports put and delete. 3. Workflow control. They describe the relationship between resources. Outbound links, like A, replace the client's current application state with a new one, i.e., you navigate to a new page. Inbound links, like image or SCRP, augment the current state by fetching another resource and incorporating it into the current view. This is also known as transclusion. Beware of fake hypermedia. Many APIs serve plain JSON where a value for a key happens to be a URL, like description http://example.com. This is fake hypermedia. The application/JSON media type doesn't define links, so a generic client has no way of knowing this is a link rather than just a string. To create a truly RESTful API, you must use a media type that has real, standardized support for hypermedia controls. Meeting the semantic challenge. Hypermedia helps bridge the semantic gap by telling a client why it might want to make a request. A client programmed to scrape images will know to follow links in IMG tags but ignore those in script tags because the tags themselves carry application semantics. While generic formats like HTML provide basic semantics, the following chapters explore more specialized formats that can convey much richer, domain-specific meanings. Chapter 5. Domain-specific designs. This chapter explores one strategy for designing a hypermedia API, creating a domain-specific media type. This approach involves designing a completely new standard tailored to solve a very specific problem. The example used throughout the chapter is a frivolous but illustrative one, a maze game API. The maze metaphor. A maze serves as a great metaphor for any complex hypermedia application, where a client must navigate a series of steps to achieve a goal. Just like a person in a maze who can only see their immediate surroundings, a client in a hypermedia API only knows about the next possible steps presented by the server in its current representation. Maze plus XML, a domain-specific media type. To represent the maze game, the chapter introduces a custom media type called Maze plus XML, application/vnd.amundsen.maze plus XML. Instead of giving the client a top-down map of the entire maze, the API provides a rat's eye view from a single cell at a time. A representation of a cell looks something like this. XML. This XML document tells the client its current location and provides hypermedia links, link tags, for the available moves, east or west. Link relations, bridging the semantic gap. The key to making this work for a machine is the link relation, the rel attribute. A computer doesn't inherently know what east means, but the Maze plus XML standard defines it. Rel equals east refers to a neighboring cell to the east. By programming a client to understand the link relations defined in the Maze plus XML specification, like north, south, east, west, start, and exit, we bridge the semantic gap. The client can then make intelligent decisions, like performing a breadth-first search to map the maze. Different clients, different goals. The power of a well-designed Hypermedia API is that it supports various types of clients with different objectives, all interacting with the same server. The chapter illustrates this with 3 different clients for the Maze API. 1. The game, a human-driven client that renders the maze cell information and lets a person decide which direction to go. 2. The map maker, an automated client that ignores the goal of finding the exit and instead tries to visit every cell to generate a complete map of the maze. 3. The boaster, a mischievous client that simply reads the list of available mazes, picks one, and claims to have solved it without ever entering. All 3 are valid clients because they work based on their understanding of the maze plus XML. The server's job is to describe the problem space, not to dictate the client's goals. Extending a standard. Even a domain-specific standard might not perfectly fit your needs. For instance, what if you want to create 3-dimensional mazes? You can extend the Maze plus XML standard by defining new link relations like up and down. However, this reveals a crucial point. Clients will only understand what they were programmed to understand. The game client would likely work with the 3D maze because it shows all available links to the human user, who can interpret up and down. The map maker, however, was built with the assumption of a 2D grid and would fail to map the 3D maze correctly, as it doesn't understand the new link relations or how to represent a third dimension. This highlights that clients are often designed with hidden assumptions about the server's behavior. A truly robust client must be programmed against the full specification of a media type, not just against one specific server implementation. When to use a domain-specific design. Creating a new domain-specific design is the most direct way to solve a unique problem and bridge the semantic gap. However, it's a lot of work. Before inventing your own, you should always look for an existing standard to reuse or extend. In most cases, it's better to add your application semantics to a more generic hypermedia format, which is the topic of the next chapters. Chapter 6. The Collection Pattern. While some problems require a unique domain-specific design, many APIs deal with a very common and recurring structure, a collection of things. This chapter explores the collection pattern, a design that shows up in all sorts of applications, from microblogs and shopping carts to weather sensor readings. Instead of reinventing the wheel every time, you can use a standardized hypermedia format designed specifically for this pattern. This saves time, leverages existing tools, and makes your API more predictable for developers. What is a collection? A collection is a special kind of resource that exists primarily to group other resources together. These individual resources are often called items, entries, or members. The representation of a collection focuses on providing links to its items, and it often includes snippets of information about each item. An important concept is that an item has its own independent existence and its own URL. It doesn't just exist inside the collection simply links to it. Collection plus JSON. Collection plus JSON, application/vnd.collection+JSON, is a modern JSON-based standard that formalizes the collection pattern. A collection plus JSON document is a JSON object with several predefined slots for hypermedia and data. href, the URL of the collection resource itself. Items, an array of the member resources. Each item has its own href, a link to the full resource, a data array for its properties like name/text, value/hello, and a links array for related hypermedia controls. Template, a hypermedia control, much like an HTML form, that describes how a client should construct an HTTP post request to add a new item to the collection. Queries, A list of hypermedia controls for searching the collection, similar to URI templates. Links, a place for other related links, such as for pagination, rel next, rel previous. The Atom Publishing Protocol, AtomPub. AtomPub, application/Atom plus XML, is the original standard for collection-based APIs, finalized in 2007. It uses the Atom XML format, which was initially designed for syndicating news articles and blog posts. In AtomPub, a collection is called a feed, and an item is called an entry. Because of its origins, every Atom entry has some built-in application semantics related to publishing, such as a title, ID, and updated timestamp. Despite this, AtomPub is highly extensible. Google famously used it as the basis for its GData APIs, representing everything from calendar events to spreadsheet cells as Atom entries with custom XML extensions. AtomPub also has a rich ecosystem of plugin standards for features like threading conversations, rel replies, and search, OpenSearch. However, AtomPub never gained widespread traction, largely because it is XML-based in a world that has come to be dominated by JSON. The semantic challenge for collections. Standards like Collection plus JSON and AtomPub do a great job of defining the protocol semantics for collections, e.g., you post to a collection to create an item. They even establish a small layer of shared application semantics, the concepts of collection and item. However, a huge semantic gap remains. A collection standard doesn't define what an item is in your specific application. A microblog post item with text and date posted fields is very different from a shopping cart item with product ID and quantity fields. While these standards provide a solid foundation, you still need to define and document your API's specific application semantics, ideally by creating a profile, as discussed in Chapter 8. Chapter 7. Pure-Hypermedia Designs. Not all API designs fit neatly into the collection pattern. For problems like the maze game from Chapter 5, or for any API that doesn't follow a common pattern, you can use a pure hypermedia or general-purpose hypermedia format. Instead of creating a brand new, domain-specific media type from scratch, this approach involves using a generic hypermedia language and adding your specific application semantics on top of it. This chapter focuses on using HTML for this purpose, as well as newer API-focused formats like HAL and Siren. Why use HTML for an API? While we usually think of HTML for human-read web pages, it has distinct advantages for machine-to-machine APIs. Rich, standardized hypermedia controls. HTML has a powerful set of built-in controls like links, forms, FRM, and embedded resources, IMG, IMScript. Flexibility. It imposes some structure but is not tied to a single problem domain. Extensibility. You can easily add your own application semantics using attributes like class, rel, and, in HTML5, microdata attributes. Tooling and familiarity. Every developer knows HTML, and every modern OS comes with a perfect debugging tool for it, a web browser. Adding application semantics to HTML. You can teach HTML to speak the language of your application by using rel link relations. You can assign custom link relations to A and link tags to describe the meaning of a state transition, e.g., rel equals north in a maze game. Class, CSS classes. You can use class names to identify specific pieces of data within your HTML, giving them semantic meaning. Microformats and microdata. These are two key techniques for adding structured, application-level semantics to HTML. Microformats. These are community-driven standards that reuse the class attribute to describe common concepts. For example, the hcard microformat uses classes like vcard, fn, full name, and bday, birthday, to mark up information in a machine-readable way. By creating an H-maze microformat, we can represent the maze game using standard HTML tags with custom classes. Microdata, a newer, more formal feature of HTML that provides specific attributes, item scope, item type, item prop, for embedding structured data. It's an improvement over microformats because it separates semantic markup from styling hooks. Schema.org is a major initiative by search engines to define a large vocabulary of microdata types for things like people, products, and events. Newer hypermedia formats. While HTML is powerful, it has limitations for APIs, e.g., forms can't trigger put or delete requests. In response, several newer formats have been designed specifically for web APIs. HAL, Hypertext Application Language, a minimalist format available in JSON and XML that defines only two concepts, resources and links. It has a single, generic link tag that can represent any state transition. However, a major drawback is that the protocol semantics, like which HTTP method to use, are not described in the representation itself, but must be defined out of band in the link relations documentation. Siren, a JSON-based format that takes a more HTML-like approach. It defines concepts like entities, which are like containers, links for simple GET navigation, and actions, which are like HTML forms and can describe any HTTP request, including post, put, delete, etc. This makes it more explicit and capable of describing complex workflows directly within the representation. By using a general-purpose hypermedia format, you can represent any API design you can imagine, and then layer on your specific application semantics using techniques like microformats or by creating a profile, which is the subject of the next chapter. Chapter 8. Profiles. After choosing a media type for your API, whether it's domain-specific, collection-based, or pure hypermedia, there's almost always a semantic gap left to fill. The media type defines the general structure and protocol semantics, but it doesn't explain the specific application semantics of your API. This is where profiles come in. A profile is a document that describes the additional semantics associated with a representation, layering them on top of the base media type. What is a profile? A profile explains the magic strings that are unique to your API, your custom link relations, and semantic descriptors. For example, in the Maze Game API, a profile would explain that rel flip means to make a post request to change the state of a switch. For an API that returns data about people, a profile would explain that the semantic descriptor FN represents a person's full name. Traditionally, this information lives in human-readable API documentation. The problem is that a machine can't process prose. The goal is to make profiles machine-readable. How to link a representation to its profile? A client needs to know which profile applies to a given document. There are several ways to create this connection. 1. The profile link relation, RFC 6906. You can include a link in your representation or in the HTTP link header with rel profile. The href of this link points to the profile document. This is the most flexible and widely applicable method. In an HTTP header, link to http:/example.com/profiles rel profile. In HTML, link rel profile href link to http:/example.com/profiles.maze. 2. The profile media type parameter. Some media types, like collection plus JSON and HAL, allow you to append a profile URI directly to the content type header. Content type, application/HAL plus JSON, profile, link to http:/example.com/profiles.maze. 3. Special purpose controls. Some formats, like HTML microdata, have their own way of linking to a profile, e.g., the item type attribute. Machine-readable profile formats. Instead of just writing prose, we can structure profiles so that a machine can understand them. XMDP, an early attempt at a machine-readable profile, designed specifically for describing HTML microformats. It's essentially an HTML document that lists the CSS classes a microformat uses. ALPS, Application-Level Profile Semantics, a more modern and flexible profile format introduced in this book. ALPS is representation agnostic, meaning a single ALPS profile can describe the application semantics for an API that serves HTML, HAL, Siren, or plain JSON. An ALPS document is a structured list of an API's semantic descriptors and link relations, along with their types, safe, idempotent, unsafe, and human-readable descriptions. This allows for the creation of generic tools and promotes the reuse of semantics across different APIs and media types. JSON LD, JSON for linking data. A W3C standard that brings the power of linked data and RDF to traditional JSON-based APIs. A JSON LD context is a separate document that maps the simple keys in a JSON object, like N, to formal URIs that define their meaning, like http://schema.org/name. This can be used to add hypermedia capabilities and formal semantics to an existing JSON API without breaking it. By using a machine-readable profile and linking to it from your representations, you make your API more self-descriptive and reduce the reliance on out-of-band documentation. This is a crucial step toward building truly adaptable and interoperable web APIs. Chapter 9. The Design Procedure. This chapter consolidates all the concepts from the previous chapters into a practical, step-by-step procedure for designing a high-quality, RESTful web API. The goal is to move beyond the common practice of creating brittle, ad hoc APIs and instead build systems that are flexible, scalable, and easy for developers to work with. The 7-step design procedure. 1. List the semantic descriptors. Start by identifying all the individual pieces of information your API will deal with, e.g., maze, cell title, switch position. This is your initial vocabulary of semantic descriptors. Group them into logical hierarchies. 2. Draw a state diagram. Map out how a client will navigate your API. Each box in the diagram represents a distinct type of representation, e.g., list of mazes, maze cell. Draw arrows between the boxes to represent the state transitions a client can make. Label these arrows with link relations, e.g., maze, start, north. Determine if each transition is safe, like get, impotent, like put, delete, or unsafe, like post. This is where you might realize a semantic descriptor is better expressed as a link relation. 3. Reconcile names. Before finalizing your vocabulary, search for existing standardized names for your concepts. Check the IANA registry of link relations, schema.org, and other semantic vocabularies. Reusing standard names, e.g., using item and collection instead of inventing your own, makes your API more interoperable and reduces the learning curve for developers. Don't simply expose your internal database field names. 4. Choose a media type. With a clear understanding of your API semantics and state transitions, you can now choose an appropriate hypermedia format. If your state diagram looks like the collection pattern, choose a format like Collection plus JSON or AtomPub. If it's a more complex branching workflow like the maze game, choose a general-purpose hypermedia format like HTML, HAL, or Siren. Avoid using plain application/JSON or application/XML as they lack native hypermedia controls. 5. Write a profile. Document all the custom application semantics you created in the previous steps. This profile should explain the meaning of your unique semantic descriptors and link relations. It's highly recommended to write this as a machine-readable profile using a format like ALPS or JSON LD. This allows for the creation of powerful developer tools. 6. Implementation. Now write the server-side code. Your server should implement the state diagram, serving representations in your chosen media type. Each representation must include the appropriate hypermedia controls to guide the client through the possible state transitions and link to the profile you wrote. 7. Publication. Publish your API's single entry point, the billboard URL. In a truly hypermedia-driven API, this is the only URL a developer needs to know to get started. Alice's second adventure. To prove the power of this approach, the chapter presents a story where a developer, Alice, encounters a completely alien and nonsensical API. The media type is custom, application/vnd.myapi.qubit, and the semantic descriptors are gibberish, QB, EBDT. However, because the API follows the rules, Alice can still figure it out. 1. The content type header tells her the media type. She looks it up in the IANA registry to find its specification and a parser. 2. The representation contains a link with rel equals profile. 3. She follows the link and gets a machine-readable ALPS profile which translates all the gibberish into human-understandable concepts, e.g., EBDT means recipe name. Even though the API was intentionally designed to be obscure, it was fully discoverable because it was self-descriptive. This demonstrates that, by embedding semantics in machine-readable formats and linking everything together, you can create APIs that are far more robust and usable than those that rely solely on external human-readable documentation. Chapter 10. The Hypermedia Zoo. This chapter provides a tour of various standardized hypermedia formats, organized by their design strategy. The goal is to showcase the rich ecosystem of existing standards, reinforcing the idea that you rarely need to invent a new media type from scratch. By choosing an existing format and adding a profile, you can leverage a solid foundation for your API. Domain-specific formats. These formats are designed to solve one particular problem and have rich, built-in application semantics. Maze plus XML, the example format for maze games from Chapter 5. OpenSearch, an XML format for describing search forms. It's what powers the search bar in many web browsers and can be plugged into other formats like AtomPub. Problem Detail Documents, a simple JSON format for providing detailed, machine-readable error messages to accompany HTTP 4XX and 5XX status codes. SVG, Scalable Vector Graphics, an XML-based image format that can include hypermedia links, making parts of an image clickable. Voice XML, an XML format for describing interactive voice response systems, phone trees, a classic example of a hypermedia-driven workflow. Collection pattern formats. These formats are designed for the common pattern of managing a collection of items. Collection plus JSON, the modern JSON-based implementation of the collection pattern, featuring items, templates for adding new items, and queries for searching. The Atom Publishing Protocol, AtomPub, the original XML-based standard for collections, called feeds, and items, called entries. It has a rich ecosystem of plugin standards. OData, Open Data Protocol, a powerful enterprise-focused standard, originally from Microsoft, that implements the collection pattern and much more. It features a rich query language, a detailed metadata document, a service description document, and can serve both JSON and Atom representations. Pure-Hypermedia formats. These are general-purpose languages with very few built-in application semantics, designed to represent any kind of workflow. HTML, the original and most powerful hypermedia format. HAL, Hypertext Application Language, a minimalistic JSON or XML format with only two concepts, resources, and links. Siren, a JSON-based format that is more expressive than HAL, with explicit concepts for actions, like HTML forms, that can describe any HTTP request. Link header, RFC 5988, an HTTP header for adding simple GET links to any representation. JSON Home Documents, a simple JSON format for creating a home page for an API that lists the available resources and their capabilities. WADL, Web Application Description Language, an early XML-based format for describing the complete protocol semantics of an API. It often functions as a static service description document. Xlink and Xforms, W3 standards for adding hypermedia links, Xlink, and forms, Xforms, to any XML document, giving it HTML-like capabilities. A cautionary tale, GeoJSON. The chapter concludes with an analysis of GeoJSON, a popular format for geographic data, to illustrate common design flaws. Lack of generic hypermedia. GeoJSON has a hypermedia control, but it can only be used for one very specific purpose, linking to a coordinate system. It has no way to represent general-purpose links, forcing API designers to embed them as plain strings in a properties object, i.e., fake hypermedia. No registered media type. GeoJSON documents are served as plain application/JSON, making them indistinguishable from any other JSON. A client has to guess the format based on the content. The lesson is to always provide a generic hypermedia control in your format and to give your format a unique media type to make it self-descriptive. Chapter 11: HTTP for APIs. While previous chapters focused on the top layer of the REST technology stack, Hypermedia, this chapter dives deeper into the middle layer, the HTTP protocol. A sophisticated understanding of HTTP's features is essential for building high-performing, secure, and robust APIs. Key HTTP features for APIs. Response codes. Don't reinvent the wheel. Use the standard HTTP status codes to communicate the outcome of a request. For example, use 400 bad requests for a client-side validation error instead of sending a 200 OK with an error message in the body. A detailed reference is provided in Appendix A. Headers. Use standard headers to convey metadata. A detailed reference is in Appendix B. Choosing between representations. When a single resource has multiple representations, e.g., JSON and XML, or English and Spanish, there are two ways for a client to choose. 1. Content negotiation. The client uses accept-headers, e.g., accept language, to tell the server its preferences. 2. Hypermedia menus. The server provides separate URLs for each representation and offers them as a choice in a hypermedia document. Performance optimizations. Caching. Use the cache control header, e.g., max age equals 3600, to tell clients how long they can cache a response, reducing unnecessary network requests. Conditional get. Use the e-tag or last modified response headers. A client can then include these values in a subsequent request using if none match or if modified since. If the resource hasn't changed, the server can respond with a 304 not modified status and an empty body, saving significant bandwidth. Compression. A client can request a compressed representation by sending accept encoding gzip. The server sends back the compressed data with a content encoding gzip header. Avoiding the lost update problem. Conditional requests can also be used to prevent data corruption. When a client wants to put or patch a resource, it should include an if match or if unmodified since header with the e-tag or last modified value it last received. If another client has modified the resource in the meantime, the server will reject the request with a 412 precondition failed, preventing the client from accidentally overriding the other client's changes. Authentication. Because RESTful systems are stateless, credentials must be sent with every request. HTTP Basic Auth. Simple username password authentication. It's insecure unless used over HTTPS and problematic because it requires users to share their primary password with every client's application. OAuth 1.0 and 2.0, the industry standard for delegated authorization. It allows a user to grant a third-party application limited access to their account without sharing their password. A client receives an access token that it can use to make authenticated requests on the user's behalf. OAuth 2.0 provides several different flows to handle various scenarios, such as web apps, desktop apps, and mobile apps. Extensions to HTTP. Patch method, an HTTP method for making partial updates to a resource. Link and unlink methods, proposed methods for managing the hypermedia links between resources directly. WebDAV, an extension to HTTP that adds file system-like operations, copy, move, lock. HTTP/2.0, the next major version of HTTP. It preserves the semantics of HTTP 1.1, methods, status codes, etc., but dramatically improves performance by features like header compression and multiplexing multiple requests over a single TCP connection. This will eliminate the need for performance hacks like bundling multiple operations into a single API call. Chapter 12. Resource Description and Linked Data. This chapter explores a different approach to structuring data on the web, primarily associated with the semantic web and linked data movements. While most of the book focuses on the representation strategy, a document at a URL describes the resource at that same URL, this chapter delves into the description strategy. A document at one URL describes resources at other URLs. The Resource Description Framework, RDF. RDF is a W3C data model for making statements about resources. An RDF statement is a triple composed of a subject, a predicate, and an object. For example, subject, http example.com/cells_m, a maze cell. Predicate, http alps.io/example/maze.title, the title property. Object, the entrance hallway. A key difference from standard REST is that in RDF, URLs are treated as abstract URIs, Uniform Resource Identifiers. There is no guarantee that a URI can be dereferenced, that is, that making a GET request to it will return a representation. This allows RDF to describe things that don't live on the web, like a physical book, earn.isbn 978-1449-35806, or an abstract concept. RDF schema. RDF schema is a vocabulary for defining other RDF vocabularies, also called ontologies. It allows you to create machine-readable profiles that are much more powerful than ALPs. For example, you can formally define a person class, state that it is a subclass of a thing, and define properties like birth date with a domain of person and a range of date. This allows for powerful automated reasoning. The linked data movement. The pure description strategy of early RDF violates many of the fielding constraints that make the web work. The linked data movement, championed by Tim Berners-Lee, aims to bridge the gap between the semantic web and REST by establishing 4 principles. 1. Use URIs as names for things. 2. Use HTTP URIs so that they can be looked up, i.e., use URLs. 3. When a URL is looked up, provide useful information using standards like RDF. 4. Include links to other URLs so that they can discover more things. In essence, linked data says that resources should have representations and that those representations should be connected via hypermedia, bringing RDF back in line with RESTful principles. Key linked data technologies. JSON LD, JavaScript for linking data, a W3 standard that brings RDF and linked data capabilities to JSON. A JSON LD document uses a special @context object to map simple JSON keys like "name" to full URI predicates like "http schema.org/name." This allows you to add formal semantics and hypermedia links to plain JSON even for existing APIs without breaking backward compatibility. Hydra, Hypermedia-Driven Web APIs, a vocabulary for JSON LD that adds the ability to describe complex API operations much like HTML forms. While JSON LD can describe links, Hydra adds supported operations that can describe any HTTP request, post, put, delete, etc., making it possible to build fully featured hypermedia-driven APIs on a linked data foundation. XRD and WebFinger. XRD is an XML format for describing resources from the outside. WebFinger is a protocol that uses JRD, the JSON version of XRD, to discover information about users based on an identifier, like an email address, account jenny@example.com, a perfect use case for the description strategy. By leveraging these technologies, you can build APIs that are not only RESTful, but also have rich, machine-readable semantics, paving the way for more intelligent and interoperable automated clients. Chapter 13, CoAP, REST for Embedded Systems. This chapter demonstrates that the principles of REST are not tied exclusively to the HTTP protocol. It introduces the Constrained Application Protocol, CoAP, a protocol designed for the Internet of Things, IoT, a world of low-power, resource-constrained devices like sensors, light switches, and home appliances communicating over low-bandwidth networks. The challenges of a constrained environment. CoAP is built for environments with severe limitations. Low power, devices may be battery-operated and need to conserve energy. Low bandwidth, networks might be slow and unreliable. Low processing power, devices have minimal memory and CPU. In such a chaotic and decentralized environment where devices from different manufacturers must discover and interact with each other without human intervention, a hypermedia-driven, RESTful architecture is the only viable approach. How CoAP works. CoAP is heavily inspired by HTTP but adapted for constrained networks. UDP-based. Unlike HTTP, which runs on the connection-oriented TCP, CoAP runs over the lightweight connectionless UDP. Binary format. CoAP messages are packed into a compact binary format to minimize their size. A method like GET is represented by a small integer, not an ASCII string. Asynchronous messaging. A request and its response are separate messages not tied together by a persistent connection. They are linked by a message ID and a token. Message types. To handle UDP's unreliability, CoAP defines message types. Confirmable, CON, the sender requires an acknowledgement, ACK, message in return. Non-confirmable, none, no acknowledgement is needed, fire and forget. RESTful features in CoAP. Methods and response codes. CoAP implements the four main RESTful methods, GET, POST, PUT, DELETE, and uses HTTP-like status codes, e.g. 2.05 content is equivalent to 200 OK. Delayed response. Because a device might need a long time to process a request, e.g. to take a sensor reading, CoAP has a built-in mechanism for delayed responses. The server can immediately send an ACK to confirm receipt and then send the actual data in a separate CON message later. Multicast discovery. CoAP leverages UDP support for multicast, allowing a new device on a network to broadcast a request, e.g., are there any light switches here, and discover other devices and their capabilities. Core link format, hypermedia for constrained devices. Because full-featured formats like HTML or JSON are too large for constrained devices, CoAP uses the core link format, application/link format. This is a very compact, text-based hypermedia format that looks like a list of HTTP link headers. An example representation of a maze cell might look like this. /cells/n, rel equals east, rt equals maze.cell, /cells/l, rel equals west, rt equals maze.cell. This format is purely for hypermedia. It represents state transitions, links, and resource types, RT. It does not contain any data payloads, like a sensor reading. The actual data would be fetched from the linked resources in a different, simple format, like plain text or a small JSON object. Conclusion: REST without HTML. CoAP demonstrates that REST is an architectural style, not a specific protocol. By adhering to the constraints of statelessness, addressability, a uniform interface, and hypermedia, CoAP brings the flexibility and scalability of the web to the challenging world of the Internet of Things, enabling a future where countless small devices can cooperate with minimal human involvement. Appendix C. An API Designer's Guide to the Fielding Dissertation. This appendix provides an analysis of Roy T. Fielding's PhD dissertation, Architectural Styles and the Design of Network-Based Software Architectures, which is the foundational document that defined the Representational State Transfer (REST) architectural style. The goal of the appendix is to translate the academic concepts from the dissertation into practical guidance for API designers. Fielding's work was not just theoretical, it was a formalization of the principles that made the World Wide Web successful and a blueprint for fixing its scalability problems, which led directly to the design of HTTP/1.1. The architectural properties of the web. Fielding identified 4 key properties that were essential to the web's success. 1. Low entry barrier. The web was easy for both users to navigate and for creators to publish content on. 2. Extensibility. The system could evolve over time without breaking. Websites could be redesigned without breaking all the world's browsers. 3. Distributed hypermedia. The control information, links, and forms is stored and served remotely along with the data, guiding the client's interaction at runtime. 4. Internet scale. The architecture supports massive, anarchic scalability, where components can be deployed and updated independently without central coordination. For web APIs, these properties are often in tension. The semantic gap, a machine doesn't understand the meaning of a link like a human does, means that using distributed hypermedia can raise the entry barrier for developers. Most current APIs sacrifice extensibility and distributed hypermedia for a lower entry barrier by providing static, out-of-band documentation. This book argues for embracing hypermedia to gain long-term extensibility. The Fielding constraints. REST is defined by a set of architectural constraints that, when applied together, produce the desirable properties listed above. 1. Client-server. A fundamental separation of concerns between the user interface, client, and data storage, server. 2. Stateless. Each request from a client to a server must contain all the information needed to understand and complete the request. The server does not store any client context between requests. 3. Cache. Responses must implicitly or explicitly label themselves as cacheable or non-cacheable to improve performance and scalability. 4. Layered system. A client cannot ordinarily tell whether it is connected directly to the end server or to an intermediary along the way, like a proxy or load balancer, which allows for flexible infrastructure. 5. Code on demand, optional. Servers can temporarily extend or customize the functionality of a client by transferring executable code, example, JavaScript and HTML. 6. Uniform interface. This is the central feature of REST and is itself composed of 4 subconstraints. Identification of resources. Each resource is uniquely identified by a stable identifier, a URI. Manipulation of resources through representations. Clients interact with resources by exchanging representations of them, e.g., a JSON or XML document. Self-descriptive messages. Each message includes enough information to describe how to process it, e.g., a content type header specifying the media type. Hypermedia as the engine of application state, HTOS. A client with a RESTful interface navigates by following hyperlinks provided in the server's responses. All application state transitions are driven by the client selecting from choices offered by the server. By understanding these foundational principles, API designers can move beyond simply using HTTP verbs and JSON and start building truly RESTful systems that are robust, scalable, and built for the long haul, just like the web itself. Glossary. This glossary provides definitions for key terms used frequently when working with RESTful web APIs, serving as a quick reference for fundamental concepts. Application semantics. The real-world meaning of a representation. For example, the application semantics of an HTML document might be to describe a person or a medical procedure. Application state. Information about the client's current position or context within an API workflow, such as which page it's on. Cache. A temporary storage for HTTP responses to avoid redundant network requests. Code on demand. A REST constraint where the server can send executable code, like JavaScript, to the client to extend its functionality. Connectedness. A more intuitive term for HTOS, emphasizing that resources are connected by links. HTOS, Hypermedia as the engine of application state. The core REST principle that clients should navigate an API by following links provided by the server in its responses. Hypermedia control. An element within a representation, like a link or a form, that describes a possible state transition, i.e., a future HTTP request. Idempotent. An operation where making the request multiple times has the same effect as making it once. PUT and delete are idempotent. Link relation. A string, like next or edit, associated with a hypermedia control that describes the meaning of the link or the state transition it will trigger. Media type. A string, like application.json or text.html, that identifies the format of a document. Profile. A document that explains the application-specific semantics of a representation, layering them on top of the base media type. Protocol semantics. The meaning of an operation in terms of the protocol. For example, get means to retrieve data, and post means to create data. Representation. A machine-readable document, like JSON or XML, that captures the current or intended state of a resource. Resource. Any concept important enough to be identified with a URL, e.g., a user, a document, an abstract idea. Resource state. The data and properties that constitute a resource at a given point in time. Safe. An operation that does not change the state of a resource on the server. GET and HEAD are safe methods. Self-descriptive messages. The principle that a message, request, or response should contain all the information needed to understand it, such as the media type. Semantic descriptor. A string that names a discrete piece of data within a representation, e.g., first name. Semantic gap. The difference between a machine's ability to parse the structure of a document and its ability to understand the document's real-world meaning. Statelessness. The REST constraint that the server does not store any client session state between requests. State transition. A change in either application state or resource state, typically triggered by a client activating a hypermedia control. URI versus URL. A URI, Uniform Resource Identifier, is a name for a resource. A URL, Uniform Resource Locator, is a specific type of URI that also tells you how to locate and retrieve the resource, e.g. via the HTTP protocol. In web APIs, almost all URIs are URLs. That's all for this episode of Geek Capsule. We hope it gave you a fresh perspective on the world of technology. We'd love to hear your thoughts, so feel free to leave a comment or share your feedback. If you enjoyed the show, don't forget to subscribe and join us next time for another essential read. Until then, keep your curiosity sparked and your mind open.